All right, let's go ahead and see how to do this. So for the region here, it's bounded by the functions y equals 1 minus x, y equal to the square root of x, and x equal to 2. We're getting this triangular-ish looking region here. It's not like really a triangle because that part's curvy, it's not straight. You have choices, but in my opinion, there is a superior choice here. The superior choice is to draw a vertical strip. So if you draw a horizontal strip, you're going to have to do two different strips. The horizontal strip would require something up here where the right was x equals 2 and the left was x equals y squared. And something down here where the right was x equals 2 and the left was whatever you get when you solve here, x equals 1 minus y. A vertical strip, on the other hand, means that the top boundary will always be y equal to the square root of x, and the bottom boundary will always be y equal to 1 minus x. So if we're going around the x-axis, our strip is perpendicular to our axis of rotation. That means we're going to have to use either the washer or the disk method. Specifically here, the washer method, because our region is not flush with the axis of, with the axis of rotation. So very generally, we're thinking about the volume being the integral of pi times your large radius squared minus your small radius squared dx. And specifically for this problem, that's going to be pi times the integral. We'll figure out the limits in a second. The large radius is the function further from the axis of rotation, which is going to be the square root of x squared. The small radius is the function that's closer, which is 1 minus x squared. Yes. We're going as far left as x equals 1, as far right as x equals 2. And that's it. That's the whole set. And if we're just asked to set up, I would stop there. I wouldn't even multiply out square root of x squared. Because leaving it like that shows that you know that oh yeah, that's the bigger radius squared, that's the small radius squared. So really, if you're asked to set it up, I wouldn't do any simplifying at all. Questions? Comments? Yeah. Which part? This region over here? So I mean I drew it before class started, but it was meant to be given in the problem. So looking at my strip here, which I can admit is a little bit hard to pick out. What I'm thinking about is the fact that this distance here is the larger radius of my washer that I would get if I rotated this thing around. And although you don't have to draw the thing I'm about to draw, we could totally think about drawing this little strip of rectangle rotated around the x-axis. So that it looks kind of like, bear with me here while I do my best to draw this. I think I might have blown it. I think I've got it. I think the perspective's a little off on that one. No, it's all right, I guess, kind of. You're getting this washer here. Like that. And the volume of that washer is the area of the larger circle. And the area of a circle is pi times the radius squared. So there's your pi times the bigger radius squared minus the area of the inner circle that isn't there. And the inner circle has, let me use a different color here. Right, the inner circle has the smaller radius right there. So big circle area minus small circle area. And then we're adding up, in quotes, right? We're integrating to get the total volume. Because again, right, we're taking those areas and we're multiplying by the thickness to get volume, and then we're adding up all the slices of volume to get the total volume. On the other hand, if we go around the x-axis, no, sorry, the y-axis, apologies, I would still prefer to use a vertical strip. Now, I'll point out, in this problem, you could totally use horizontal strips for both of them. And for the first part, do the shell method with 2 intervals. And for the second part, do the washer method with 2 intervals. I would prefer to use 1 interval if I can. So I'm going to continue to use a vertical strip here. And now when I go around the y-axis, I'm thinking of, well, this strip. Yeah, I guess I can draw this down here. I'm thinking of this little strip getting rotated around the y-axis and getting a cylindrical shell. You do not need to draw these pictures when you do this. I'm drawing them for you so that you can visualize what is happening. So there's my cylindrical shell, and the volume of that shell is the circumference of the cylinder, 2 pi r, times the height of the cylinder, times the thickness of the cylinder. But the radius is just how far we are from the axis of rotation. So our radius here is just x. The height is the height of the strip. So the height is going to be the top function minus the bottom function, square root of x minus 1 minus x. And the dx is just the dx, the thickness. So then the total volume, again, quote unquote, adding up all of the shells, or the volumes of the shells, is going to be the integral, also from 1 to 2, because the region didn't change. This little strip still goes as far left as 1, as far right as 2, of 2 pi times x times square root of x minus 1 minus x. Yes. And typically people do write the 2 pi out in front. I just haven't been doing that because normally the 2 pi would live out in front. Don't forget it. It's easy like halfway through the problem to forget the 2 pi is there, and then they're like, oh, why am I off? So that's how we set this one up using the shell method. What else to say? I don't have anything to say. All right. Questions? Yeah, I mean, you're welcome to ask questions, but I'm going to say it every time. Yeah.
Why do we integrate in terms of x with both of them, even though we rotate around?
Question. The answer is because I wanted to, because it feels easier to me. Now let's do it the other way to see how you do it the other way. I do think it's worth looking. Let's look at the same region. We're going to go around the x-axis again. But now we're going to use a horizontal strip. It's going to be a little bit more work. So I'm going to draw a very kind of a less nice version of this. This pen seems like it's. Okay, well, here we go. So here's my region again. I guess I'll try and draw it similarly here. Square root of x, my x equals 2, and my 1 minus x. I have a ruler. There we go. So same region. And now we're going to use a horizontal strip. Well, I said we're going to use 2 different horizontal strips. And this is actually the reason why I decided to do it the other way. So I'm using a horizontal strip there, and then I'm using a horizontal strip there. So if we're going around the x-axis, I'm going to observe that my strip is parallel to my axis of rotation, meaning I'm going to have to use the shell method. So we're going to have a breakpoint here at y equals 1. That, right, that point there is 1, 1. So for y between 0 and 1, we can see that we're going to use this little strip rotated around the x-axis. So the volume of my shell, again, is 2 pi r times h times dy in this case. Right? Thickness is dy, not dx. Small change in y there. Now, for this shell, my radius is y. It's just how far the strip is from the axis of rotation. So we're at a height of y. You guys see that okay? And then our height is just the length of the strip. So right minus left is going to be x equal to 2 minus x equal to 1 minus 1. There's your height and still dy. So this first half where y is between 0 and 1, we're going to get the integral from y equals 0 to y equals 1 of 2 pi times y times 2 minus 1 minus y. I'm very aware that we could simplify this to be something nicer, but again, we're just setting it up, so there's no reason to simplify. Yeah. Well, the height's not one. So the radius. So what we're doing when we do this is we're imagining that our strip is some distance from the axis it's parallel to. So this horizontal strip is some height of, I know I'm using the word height there, but not in the same context, some height above the x-axis. And that's going to be y, where for this strip, y is going to vary between 0 and 1. So this strip could be at a height of 0.1 or 0.2, right? Whereas in the previous one, when we were doing the shell method, we were imagining this vertical strip at a distance of x from the y-axis when we were doing it with the shell method. And typically, if you're going around a normal axis, meaning either the y-axis or the x-axis, your radius for the shell method is just the variable you're using. If you're going around the y-axis, it's going to be x. If you're going around the x-axis, it's going to be y. Right? Because if you're going around the y-axis and you're using the shell method, your strip better be vertical, meaning you're using x's, like this picture here. If you're going around the x-axis and you're using the shell method, your strips better be horizontal, like we have here, because your strips must be parallel if you're using shell. Parallel shell, parallel shell, parallel shell, parallel shell. Okay, so that's that's part of it, but then we also have to add on the section where y is between 1 and the square root of 2. At that point there is 2 comma root 2. So when y is between 1 and the square root of 2, we're still going to have the same setup. The volume of our shell is still the same generic 2 pi times the radius times the height times dy. But now the height part, the length of our strip is going to be different. We're going to get 2 pi still times y, because we're still imagining this as the height of y. And then our height, sorry, I know I'm using the word height twice here. I should really call it length. The length of our horizontal strip there is the right function, x equals 2, minus the left function, x equals the y squared. Right, this was y equals square root of x, and I didn't write it down, but y equals square root of x certainly is the same as x equals y squared times dy. And then the total volume there would be the integral from 1 to root 2 of all that. 2 pi times y times 2 minus y squared dy. And so then the total volume around the x-axis would be these integrals added together. So 2 pi times the integral from 0 to 1 of y times 2 minus 1 minus y plus 2 pi times the integral from 1 to root 2 of y times 2 minus y squared. And so you hopefully can see why you might choose to do it the other way, because it's certainly a bit more effort to do it this way. Not impossible, and sometimes doing it this way is nicer because maybe the function is nicer to integrate. Like, it's probably a little bit nicer to integrate this than it was the other thing, but choices have consequences. Okay, let's look at the other, well, actually I should say, questions about what we've done here before we also go around the y-axis using the disk method. Sorry, shell, washer method, not disk, washer. Okay, let's washer it up. I'm going to try not to draw the picture here. I'm just going to say around the y-axis, use the washer method. We're still going to have to break it up into the two sections. So for the y between 0 and 1 section, we're going to have usual formula, right? It's going to be the volume of our washer is pi times the big radius squared minus pi times the little radius squared, all times the thickness. And for our region here, our big radius is x equal to 2. Our little radius is the closer function, x equal to 1 minus y. Right? This blue line here, which is y equal to 1 minus x, if I solve for x, I do get x equal to 1 minus y. And let's just do the other part before we do this part. So then for the y being between 1 and the square root of 2, same deal. We're still going to find the volume of a washer to be pi times the big radius squared minus pi times the little radius squared, all times dy. And then in this case, our big radius is still x equal to 2. But now our little radius is this red function, which is x equal to y squared. Questions about that specifically? I can't stress enough how much easier it is to do this problem when you graph it, right? Graphing the region makes all these things fairly easily visible. If you try to do it without graphing, it's going to be hard. So take the time, graph the thing. Usually the functions are relatively basic, like square roots or x squared or x cubed, right? They're not like super complicated things that have weird asymptotes and stuff like that. They're usually normal-ish functions, for lack of a better phrase. All right, so our total volume now is going to be this volume, which is going to be the integral from y equals 0 to y equals 1 of pi times our big radius squared minus our little radius squared, dy, plus the volume of this part, which is going to be adding up all the slices, pi times the integral from y equals 1 to y equals square root of 2 of your big radius squared minus your little radius squared. That's how you'd set it up using the less easy way, but still valid. And either way you do it, the way you calculate the volume around the x-axis should be the same either way, and the way you calculate the volume around the y-axis should be the same either way. Not the same as each other, but like the x-axis one should be the same, and the y-axis one should be the same. All right, fun. Well, they were fun, but moving on. So we got like 3 other things to talk about today. Let's start with arc length. Let me zoom out a little bit here. Whoops. Too crazy here. All right, let's see if we can get in frame. Okay. Arc length. So one way about talking about arc length is imagine you've got a particle moving along a curve. So you've got some curve, maybe it looks like that, and you've got some particle that's moving in this direction. So it just keeps going on and on and on. And we're trying to figure out kind of how far it's gone. So we're going to call the arc length our particle travels. We will call S. So the velocity of the particle is the derivative of S, ds dt. And if we zoom in on just a tiny little portion of this here, maybe we look at like this little segment, right? Oh, can I make that a little bit redder there? Yeah. Look at that little segment there and think about trying to find the length of this, maybe this small change in S. Let's call that ds dt. Well, this part here is really a change in y, and this part here is really a change in x. So you've got like the velocity in the x direction, the velocity in the y direction being components of the vector that's the velocity in the s direction. But that looks like a right triangle to me. And we can use the Pythagorean theorem to say that, well, ds dt squared is equal to dx dt squared plus dy dt squared. And manipulating things a bit, you can say that this ds dt is equal to the square root of dx dt squared plus dy dt squared. And then bringing the dt over to the other side, ds is equal to the square root of dx dt squared plus dy dt squared dt. And then finally, if you integrate ds, or 1 times ds, that's just your arc length s, and that's going to be the integral of the square root of dx dt squared plus dy dt squared dt. And this is, and then you'll have some limits of integration, which we'll talk about in a minute. And this is one of 3 versions of the arc length formula. They're all really the same, but they all look a little different. So this is the general idea. When you're integrating, when you're trying to find arc length, I'm always going to think about it as integrating ds, where ds is equal to this expression or a couple other things we'll get to very soon. Well, let's do one example like this that's a little bit funky. So let's say that we wanted to find, right here, we want to find the length of, sure, the curve defined by, let's make this less terrible than that problem is. X equal to sine of t and y equal to cosine of t defined by, oh, sorry, on the interval from t equals 0 to pi. Now I like this example because this is something that we'll graph in just a second. So, yeah, this process can be a little bit weird, but at the end, we can just throw it all into the form. So what we're going to do here is we say, well, great. I know that my arc length S is going to be the integral from 0 to pi of the square root of the derivative of x squared plus the derivative of y squared, which is going to be the integral from 0 to pi of the square root of, let's see, the derivative of sine is cosine, so it'd be cosine squared. And the derivative of cosine is negative sine, so that's going to be plus negative sine of t squared dt. But then, what do we have inside that square root? We have cosine squared of t plus sine squared of t. And what's cosine squared of t plus sine squared of t always equal to? Just 1. So we have the integral from 0 to pi of the square root of 1. The antiderivative of 1 is t from 0 to pi, and then you plug in and you get pi minus 0, which is pi. And this is a relatively easy example. But what I want to point out is all we've done here is we said, well, if you actually graph this, x equal to sine of t, y equal to cosine of t, that's just the graph of a circle of radius 1. In fact, we want to plot some points here. If t is 0, sine of 0 is 0, cosine of 0 is 1. So we're starting at the point 0, 1. And then if t is pi over 2, sine of pi over 2 is 1, cosine of pi over 2 is 0. So we're moving over here to the point 1, 0. And then if t is pi, sine of pi is 0, cosine of pi is negative 1. So we're moving down to here. So we just found the length of this circumference of half of a circle of radius 1. Oh, we know how to find the circumference of a circle. Circumference is 2 pi times the radius. So the circumference of a circle of radius 1 is 2 pi. So half the circumference of a circle is just pi. All I'm trying to display here is that this formula actually works, right? Finding the arc length using this seemingly complicated formula works for something that we already know the arc length of. It would also work for lots of things that we don't already know the answer to. So let's look at some different examples. Yeah, we might come back. That one's a little tricky. Much of the time, I would say your arc length question is not going to be phrased in terms of a parametric function where everything's in terms of t. It's going to be phrased as either y is a function of x or x is a function of y. So if the curve is given by y equal to some function of x, we can easily manipulate our previous arc length formula. By letting x equal t and y equal f of t. Let me show you what I mean. So let's say, for example, we have that y equals x to the 3/2. And sorry, let me put some integration here. Sure. From 0, 0 to 4, 8. And we would like to find the arc length. So whichever variable looks like the independent variable, we're going to set equal to t. So we're going to think of this as x equals t and y equals t to the 3/2. So that then we can rewrite our formula, the integral from t equals 0 to t equals 4 of the square root of dx dt squared plus dy dt squared. Well, if x is t, then dx dt is just 1. So this is going to be the same as writing the integral from, I'll deal with it for a second, 1 squared plus dy dx squared dx from x equals 0 to x equals 4. So if you have y as a function of x, this is the version of the formula we have. The square root of 1 plus the derivative squared. Then we're going to integrate that. But you kind of see how we're going from this formula and say, oh yeah, if x equals t, that part's just going to be 1. And if y equals a function of x, we're just going to get the derivative of y squared. All right. So then I feel like these problems, once you kind of see the formula a few times, they feel very kind of plug and chug. You go, okay, here's the thing, find the derivative, do what you need to do, and then see what happens. So here, my dy dx is going to be the derivative of x to the 3/2 is 3/2 x to the 1/2. So then when we find this arc length here, this is going to equal the integral from 0 to 4 of the square root of 1 plus 3/2 x to the 1/2 squared, which is really just the integral from 0 to 4 of the square root of 1 plus 9/4 x, which I think we could do without a u substitution if we rewrite it. Let's rewrite it as the integral from 0 to 4 of 1 plus 9/4 x to the 1/2 power. We could do a u sub and let u equal 1 plus 9/4 x, but I feel like we've done enough of these where we know that if it's just a multiple of x, you just use whatever rule applies, in this case, the anti-power rule. We're going to get our stuff, 1 plus 9/4 x to the 3/2 power times 2/3. And then what else do I need to divide by? The coefficient of x, which is 9/4. So I'm going to divide by 9/4 or multiply by 4/9. The reason this works is because if we took the derivative of this using the chain rule, we'd end up multiplying by a 9/4, which would cancel out the 4/9. And then we simplify and plug in. So we've got 2/3 times 4/9 is 8/27 plus u. That's 1 plus 9/4 x to the 3/2, 0 to 4. And we end up getting, let's see, plug in 4, you get 8/27 times 1 plus 9 to the 3/2 minus, bless you again, 1 plus 0 to the 3/2, which is not a particularly nice number. And most of these arc length problems, the answer is not going to turn out to be very nice. It's usually going to be something kind of like that. So let's do another one. There's one particular style of arc length question that I think comes up a lot. It'll be the next one. Yeah, sure. So let's look at, say, finding the arc length of y equal to x to the 4th over 4 plus 1 over 8x squared, where x is between 1 and 2. So there's not a lot to do here other than find the derivative, square it, and throw everything into the formula. Let's go ahead and find the derivative over on the side. So our derivative dy dx is going to be, I might rewrite this as 1/4 x to the 4th plus 1/8 x to the negative 2nd, just to make it easier to differentiate. So my derivative is going to be 1/4 times 4x cubed, which is just x cubed. And then 1/8 times -2 is negative 1/4 x to the negative 3rd. And then we're going to square them. And I kind of like doing this work on the side, especially when it's something where something kind of cool happens like this. I know it hasn't happened yet. It's about to happen. So if we square this, here's the important part. So we're going to get x cubed squared, so x to the 6th. And then we're going to get 2 times x cubed times negative 1/4 x to the negative 3rd plus negative 1/4 x to the negative 3rd squared. So 1/16 x to the negative 6. And the important thing to see here is that the middle term simplifies to negative 1/2. And that is definitely by design. But let's check it out to make sure. X to the 3rd times x to the negative 3rd is x to the 0th, and 2 times negative 1/4 is negative 1/2. Okay, here's why this is important. So when we actually find the arc length, it's going to be the integral from 1 to 2 of the square root of 1 plus our dy dx squared dx. That's going to be the integral from 1 to 2 of the square root of 1 plus x to the 6th minus 1/2 plus 1/16 x to the negative 6th. And when you add 1 to that, the only thing that changes is negative 1/2 plus 1 becomes positive 1/2, which means this thing factors really nicely. Like we already kind of know how it factors. So this is going to be the integral from 1 to 2 of the square root of x to the 6th plus 1/2 plus 1/16 x to the negative 6th. And that's exactly going to be the integral from 1 to 2 of the square root of x cubed plus 1/4 x to the negative 3rd squared. Yes. This happens a lot where the thing you've squared out has a negative 1/2 as the middle term. You add 1 to it, the middle term becomes a positive 1/2, and then it factors essentially the same way as you started, except that now instead of having a minus sign in the middle, you have a plus sign in the middle. Happens very often. We often pick problems like this on purpose so that it happens like this. So then the square root of this stuff squared, it's just stuff. So this ends up equaling, I keep running out of room here. This is going to equal the integral from 1 to 2 of just x cubed plus 1/4 x to the negative third. And then we anti-differentiate that, and we get x to the 4th over 4 minus x to the negative 2 over 8 from 1 to 2. It kind of feels like we did a whole lot of work to end up at almost exactly the same function we started with. You can't see, sorry. Almost the same. We still have to do the work. So even though you might see this, be like, I'm pretty sure I know what's going to happen. The expectation is you still do this work to get to this end place here. So then we plug in our values, we get 2 to the 4th over 4 minus 2 to the negative 2nd over 8 minus 1 to the 4th over 4 minus 1 to the negative 2nd over 8. Whatever that ends up equaling. So just to make sure everyone's on board with this, I just want to point out that if you look at this part here, this x to the third plus 1/4 x to the negative third squared really is, we FOIL this out, x to the third times x to the third is x to the 6th. X to the third times 1/4 x to the negative third is just 1/4. And 1/4 x to the negative third times x to the third is also 1/4. And then 1/4 x to the negative third times 1/4 x to the negative third is 1/16 x to the negative 6th. And those are exactly the same. X to the 6th plus 1/2 plus 1/16 x to the negative 6th. So, but you don't have to show all this work. You know that when you switch the sign in the middle part, you're just changing the middle sign of how you factor this. Let's do one more similar to this, and then we'll talk about surface area. We got time. Yeah, we got time. Let's see. Let's look at that one. So let's say we want to find the surface area. So where'd you go here? Yeah, or find, sorry, not surface area. I'm sorry, I'm getting ahead of myself. Find the length of the curve x equal to, where'd you go here? Y cubed over 6 minus, sorry, plus 1 over 2y, where y is between 2 and 3. So our length is going to equal the integral from 2 to 3 of the square root of, oh, I have x as a function of y now. The same formula is applicable, except instead of 1 plus dy dx squared, it's going to be 1 plus dx dy squared. Because x is a function of y, so having y is a function of x. And that'll be a dy, not a dx. It's essentially by taking the same parametric formula and said y was equal to t and x was equal to that function of y as a function of t. Okay, so let's do all the work on the side. So dx dy is going to be the derivative of y cubed over 6. That's going to be 3y squared over 6. And the derivative of 1/2 y to the negative 1 is negative 1/2 y to the negative 1. So here's what I have noticed as I do these problems. If you see that after you take the derivative, you have two terms where since you have the opposite powers, it means when you square it and you multiply those things together, those opposite powers are going to add to 0. And your middle term is going to be just a constant. So when we square this, dx dy squared, which is going to be, let's simplify this a bit, y squared over 2 minus y to the negative 2 over 2 squared. We actually want to multiply it out. gonna get y to the 4th over 4. These two terms multiply, so let's actually draw that here. And that times that is going to be y to the 0th over 4. And that times that is also going to be y to the 0th over 4. And that times that is going to be positive. Oh, sorry, I made a small mistake here. This should be negative y to the 0th over 4 and then negative y to the 0th over 4. Sorry. And then finally, that times that is going to be a positive y to the negative 4th over 4. So that's going to simplify as y to the 4th over 4 minus 1/2 plus y to the negative 4th over 4. And then if we add 1, so then we'll note that y to the 4th over 4 plus 1/2 plus y to the negative 4th over 4 is going to factor as y squared over 2 plus y to the negative 2 over 2 squared. We haven't gotten there yet, but I'm just saying, oh, I know that's going to happen. So now let's write out the formula here. This is going to be the integral from 2 to 3 of the square root of 1 plus our derivative squared. And since I've already done all this work over here, let's just cut to the chase. Let's see, we're down to here. That's going to be the integral from 2 to 3 of the square root of 1 plus y to the 4th over 4 minus 1/2 plus y to the negative 4th over 4. And then we're adding the 1, and 1 plus the negative 1/2 becomes a positive 1/2. That's the integral from 2 to 3 of the square root of y to the 4th over 4 plus 1/2 plus y to the negative 4th over 4. But we know that that inside part is really y squared over 2 plus y to the negative 2 over 2 squared. So this is going to end up being the integral from 2 to 3 of just y squared over 2 plus y to the negative 2 over 2 dy. And then we can integrate and get y cubed over 6 minus y to the negative 1st over 2 from 2 to 3. And so we see again that we essentially, after doing all of this, end up with virtually the same function we started with, except the middle sign has switched from positive to negative, or from negative to positive. Because this 1 over 2y is the same as y to the negative 1st over 2. Again, it feels almost like, why would you do all this? Well, it doesn't always work out. So, and then we plug in and we get 27 over 6 minus 3 to the negative 1 is 1/3 times 1/2 is 1/6. And then plugging in 2, you get 8 over 6. Yes. Minus 2 to the negative 1/2 is 1/2 times 1/2 is 1/4. A little bit, no, kind of a lot. So not every arc-length problem works out like this, but a lot of them do. So you should definitely look for, when you're multiplying this out, if there's a negative 1/2 in the middle, you'd be like, oh yeah, I'm going to add 1, get positive 1/2. Things are going to factor out essentially the same way they were before, except instead of having a minus sign there, I'm going to need a plus sign there, or vice versa. If you'd had a plus sign there, you'd have a minus. Although usually it's a minus to a plus, because it has to be a minus 1/2 that you're adding 1. Right. Let's talk about surface area. Surface area and arc length really go hand in hand because they're really kind of the same. It's just building upon the arc length idea. So for surface area, we're gonna, yeah, let's do that. So I know we're going kind of fast. Unfortunately, there's a lot of things to talk about. So let's talk about surface area for a brief bit here. So let's say we want to find the surface area of the quote unquote bowl formed by revolving the curve y equals x squared from x equals 0 to x equals 2 about the y-axis. So we've got the parabola y equals x squared, looking like it usually does. And then, we're not revolving a region to get the solid. We're revolving a curve to get the surface of that solid. I'm going to revolve this around, and I'm going to get, and then it looks like this. We want to find the surface area of this bowl, this hollow, right? It's actually a bowl, right? It's not like a solid. So the idea is we're going to take a small little portion of our length of our curve, and we're going to think about rotating that around the same axis. I like to think of it as a rubber band. So we want to find the surface area of our rubber band. So the surface area of our rubber band, well, it's going to be the circumference of the rubber band times the thickness of the rubber band. But the thickness isn't a dy or a dx. It's a ds. Because we didn't move straight up and down or straight left and right. We moved in a diagonally kind of. So it's some small change in the length of the curve. So that is generally how I think about the surface area of this one rubber band. And then we're going to add up all the areas of the rubber bands. So the total surface area is going to be the integral of our 2 pi r times our ds. This is where things get a little bit weird. You can kind of do this in whatever way you like. What I mean by that is you can do this in terms of x or in terms of y, no matter which axis you're going around. Since I have already written the function in terms of x, I'm going to try and keep things in terms of x. So in that sense, I'm imagining that the radius of this rubber band is just x. I want to keep things in terms of x. And my ds, well, ds is what it always is. Well, that's not the right thing to say, because ds could be one of 3 different things, but ds is always the square root of 1 plus the derivative squared times your d whatever. So in this particular example, we're going to write that our surface area is equal to the integral of 2 pi times our radius x times the square root of 1 plus the derivative of my function squared, where that 2x there is my dy dx. And my limits of integration are from x equals 0 to x equals 2. And then this problem is not terrible. It's the integral from 0 to 2 of 2 pi times x times the square root of 1 plus 4x squared. And we can definitely do a u substitution. So we can let u equal 1 plus 4x squared. Or du is 8x times dx. I have an x times dx. So 1/8 du is equal to x times dx. And I can rewrite this integral as 2 pi times the integral of x dx is 1/8 du. And then my square root of 1 plus 4x squared is the square root of u. And since it's a definite integral, let's go ahead and change the limits of integration as well. If x is 0, u is going to be 1 plus 0, which is 1. If x is 2, u is going to be 1 plus 4 times 2 squared, which is 1 plus 16, which is 17. Then we're integrating u to the 1/2. The 2 pi times 1/8 is pi over 4. The integral of u to the 1/2 is u to the 3/2 times 2/3 from 1 to 17. So we end up with pi over 6 times 17 to the 3/2 minus 1 to the 3/2. Kind of a lot. Sorry, it's shot water. So depending on the context of the problem, you might think of the radius as just your variable x. Specifically, if you're revolving around the y-axis, your radius could just be x. Or if I was revolving around the x-axis, my radius could just be y. Or, let's see what happens if we go around the x-axis. How much time do we got? Okay, we got time. So, this was part A, I guess. Part B, what if we revolve around the x-axis? So same curve, y equals x squared from x equals 0 to x equals 2. It's about like that. But now we're revolving that curve around the x-axis. So we have shape, surface that looks like this. And now our rubber bands look like this. Same idea for the surface area. The surface area of my rubber band is going to still be 2 pi times the radius times the ds. So one way to think about this is, well, now if I'm going around the x-axis, my radius of my rubber band is y. So I could think of this as 2 pi times y times ds. But I know what y is in terms of x, right? This function is y equal to x squared. And if I want to just keep things in terms of x, I can by saying, well, the radius is y, and y is equal to x squared. So my surface area of my band is actually going to be 2 pi times x squared. And then I'll use the x version of ds, which is 1 plus the derivative squared. So then we can find the surface area. We can set up the integral for the surface area as the integral still from x equals 0 to x equals 2 of 2 pi times x squared times the square root of 1 plus 4x squared. And unfortunately, we don't yet have the means of actually calculating this antiderivative. It would require trig substitution, which we haven't learned yet, but we will. So let me take a pause for a moment here. Actually, before I pause, let me point out that we could have set this one up in terms of y if we wanted to. If I had decided instead to do this one in terms of y, we could say that our radius was y, and then if we solve for x as a function of y, instead of saying y equals x squared, that's going to become x equal to the square root of y. And then my dx dy is 1/2 y to the negative 1/2. So if we want to set the same surface area integral up in terms of y, it's going to be 2 pi times my radius, which is just y, times my ds, which is the square root of 1 plus my dx dy squared. And then y would go from 0 to 4 instead of 0 to 2. So I want to really point out these two integrals represent the same surface area. Doing it this way in terms of x, my radius is x squared, and there's my ds. Doing it this way in terms of y, my radius is just y, and there's my ds. It's a little bit weird. You can always make the change. I should say, if you can easily go between y as a function of x or x as a function of y, like going from y equals x squared to x equals square root of y, then you can kind of choose whichever way seems better to you. Sometimes, though, it's kind of impossible to solve for one function. Let's look at, we got them. So let's look at the following example. Let's say we want to find the surface area of the function y equal to the square root of 2x minus x squared, where x is between 0 and 2, revolved around the x-axis. Okay, so this function looks vaguely like this. It's got intercepts at 0 and 2, revolving it around this way. So it kind of looks like a football. I don't know, kind of football-ish. Again, we're looking at the area of my rubber band. So every time I do a problem like this, I'm always thinking of the surface area of my rubber band as 2 pi times my radius times my ds. That is always the starting place for these surface area problems. And then we get to decide what context we want to do things in. To me, it looks like things are set up in terms of x already. So I want to do things in terms of x. So I'm going to say that my surface area is going to be the integral of 2 pi times, I know I said I am going to do things in terms of x, but I know if I'm going around the x-axis, I'm thinking of my radius as y. And then replacing y with what it's equal to. So my radius here is going to be the square root of 2x minus x squared. That is my radius, which is equal to y, which is what y is equal to. And then my ds is the gnarly part. It's 1 plus my derivative squared. Let's find the derivative over here. Let's see, so my y is equal to 2x minus x squared to the 1/2 power. My dy dx, or my y prime, is going to be 1/2 times 2x minus x squared to the negative 1/2 times the derivative of the inside, which is which is 2 minus 2x. Okay. It might be worth our while to simplify that. Let's take a look. If we look at this, that's going to be, well, let's see, 1/2 times 2 minus 2x is just 1 minus x. And this 2x minus x squared to the negative 1/2 is really dividing by the square root of 2x. And then we're going to square that. So we're going to get, we're going to get 1 minus x over the square root of 2x minus x squared squared, which looks pretty terrible. But don't give up hope, because this is, oh, then we're going from x equals 0 to 2. So something that happens a lot is when you have a square root times a square root, you actually want to put them together in one square root. So let's reimagine this as the square root of this 2x minus x squared times 1 plus, I'm going to square this out and get 1 minus x over 2x minus x squared. And that seems like it's going to be awfully convenient Oh, sorry, that's 1 minus x squared, apologize. When I multiply this through, when I multiply this to the second part, the 2x minus x squared is going to cancel. So look what we get. We get 2 pi times the integral from 0 to 2 of the square root of 2x minus x squared times 1 plus 2x minus x squared times some stuff divided by 2x minus x squared is just the stuff on top. And then if we multiply it out, interesting. Oh yeah, sorry. Sure, I will do it that way. Look what happens. We get 2 pi times the integral from 0 to 2 of the square root of 2x minus x squared plus 1 minus 2x plus x squared. And the 2x's cancel and the x squareds cancel. And you get 2 pi times the integral from 0 to 2 of 1. So if you persevere, sometimes the integrand becomes super duper simple. And that's just going to be 2 pi times x evaluated from 0 to 2, which is just 4 pi. Sometimes they turn out really nice. Sometimes they're terrible. All right. So there's surface area in a nutshell. And yeah, it's kind of, so basically once you're given an axis to go around, you can always either do it in terms of x or in terms of y. We could have done this one in terms of y if we really, really wanted to. We would have had to solve for x as a function of y, though, which would have been a little bit gnarly, but not impossible. Okay, 4:15. Guess we should talk about integration by parts. Right, because people are starting to talk about integration by parts. I know some people are. People wrote that, so I know it's a lot in one day. We can definitely, on Thursday, we can revisit these things again, but I do feel like I at least owe you a few integration by parts examples because you're going to be there. So, integration by parts, which is often abbreviated as IBP. So what I would say about integration by parts is it is exclusive, almost exclusively used on what I usually refer to as a mixture type of integral. So we use it on mixture integrals, meaning you have two types of functions multiplied together. For example, the integral of x times e to the 2x, or the integral of x squared times cosine of 3x, or the integral of x cubed times the natural log of x, or the integral of x times the inverse tangent of x, or the integral of e to the x times cosine of x. Each of these I would think of as a mixture. You have a mixture of x to a power and an exponential, or x to a power and a trig function, or x to a power and a log function, or an exponential and a trig function, or an x to a power and an inverse trig function. You have two types of functions multiplied together. And it is important that they are multiplied together, because integration by parts is really about having two functions being multiplied together, because it's really undoing the product rule. It's not exactly the anti-product rule, but it comes from the product rule. So here's where integration by parts actually comes from. So if you start with the product rule, and we're going to use the typical letters, which unfortunately are U and V, which we already use the U for U substitution, and they look kind of similar if you're not careful. So what we're starting with is the derivative of U times V. And it's equal to U times the derivative of V, which I'm going to write as dV instead of V prime, plus V times the derivative of U. And then we're going to anti-differentiate both sides. So the antiderivative of U times V prime is equal to the antiderivative of u times dv plus the antiderivative of v times du. And then the antiderivative of the derivative is just the thing. So the antiderivative of the derivative of u times v is just u times v. And we get u times v equal to the integral of u times dv plus the integral of v times du. And then we subtract the integral of v du from both sides to get that u times v minus the integral of v du is equal to the integral of u times dv. The idea behind integration by parts is that we're going to be starting with the right-hand side here. You're going to have some awful integral of u times dv. And the whole idea is that we're going to rewrite it so that we have a new integral that we're still going to have to integrate that's going to be easier to deal with. That's the whole purpose of integration by parts. So let's look at this first example, actually. Let's say we wanted to try and find the integral of x times e to the 2x. So if we're thinking we're going to use integration by parts, our job is to identify the parts. So if we're doing integration by parts, we have to figure out what the u and the dv are in our integral. So some rules of thumb. U should be something that gets simpler when you differentiate it. And dv should be something that doesn't get more complicated when you anti-differentiate it. So here, I would make the choice of letting u equal x, because its derivative is simpler, it's 1. I would make the choice of letting dv be the rest, which is e to the 2x, because the antiderivative of e to the 2x is essentially still e to the 2x. It didn't really get more complicated. So our choice here is that u is going to be x and dv is the rest. And usually that's how I'm going to think about it. I'm looking for what u is going to be, and then dv has to be everything else. So that u multiplied by dv is the entire integral, including the dx part. So we're going to write down u. U is equal to x. dv is equal to e to the 2x times dx. And then we're going to find the other two pieces. Du, well, the derivative of x is just 1. So du is 1 times dx. And v, which is the antiderivative of dv, is going to be e to the 2x divided by 2. And then we're going to plug all that into the formula. So our integral of u dv is equal to u times v. I'm not actually writing u times v. I'm using the things that u and v are equal to, minus the integral of v times du. Now, it's okay to write out the formula first if you want to. Right, there's my u times v minus the integral of v times du. So again, the point of this is that we're starting with this. We're rewriting it as this, which it is in fact equal to. But this new expression, specifically the integral, is something we are able to find the integral of. We know how to anti-differentiate e to the 2x times 1/2. So let's simplify this a tiny bit. This is going to be equal to 1/2 times x times e to the 2x minus, I'm going to pull out the 1/2, the integral of e to the 2x dx. And the integral of e to the 2x, again, is e to the 2x divided by 2. So this ends up equaling 1/2 times x times e to the 2x minus 1/2 times another 1/2 times e to the 2x plus c. And we can check. You don't have to check, but if we check and take the derivative of all this, we should get back the function we started with. Let's check. If I take the derivative of 1/2 times x times e to the 2x minus 1/4 times e to the 2x plus c, I'm going to have to use the product rule for this first part. So I'm thinking about it as this times that So the derivative of 1/2 x is 1/2 times the other part, e to the 2x, plus 1/2 x times the derivative of e to the 2x, which is e to the 2x times 2, minus the derivative of 1/4 e to the 2x is 1/4 e to the 2x times 2. Derivative of c is 0. And look, the 1/2 times e to the 2x and the minus 1/2 times e to the 2x add to 0. And we're left with exactly 1/2 times 2, which is x times e to the 2x, which is exactly the function we were anti-differentiating in the first place. So integration by parts does work. There is a pretty good way of deciding what you might want to try to let u equal through an acronym. So the acronym is u should equal light. It's better in the 16 series where we don't really talk about inverse trig functions, and then it's a nice acronym, it's just late. But for us, we have to include inverse trig functions. So when you're trying integration by parts, if you think it should be integration by parts, first you're going to try and let u equal a logarithmic function if you have one. If you don't have a logarithmic function, you're going to try letting u equal an inverse trig. If you don't have either of those, you try letting u equal any power of x. If you don't have either of those, you try letting u equal the trig function. If you don't have any of those, you almost never let u equal e to the x. Usually you're never letting u equal an exponential function like x. So for example, if we were given, say, the integral of x to the 5th times the natural log of x dx, what should I be letting u equal? Well, according to my list here, natural log of x. And then I don't even have to think about what dv is. It's already predetermined for me. Once we have picked u, dv is the rest. Everything left. So dv is going to have to be x to the 5th times dx. And if you multiply those together, you have to get that back. So if you're thinking integration by parts, there shouldn't be any like addition or subtraction in your integral. It's really just purely multiplication of functions. My du is going to be 1 over x dx. Oh, good. 1 over x is certainly simpler than natural log of x. And my v, okay, my antiderivative is slightly more complicated, but in the grand scheme of things, x of 6 is not a whole lot more complicated. So then we're going to rewrite this integral as, okay, here's an acronym coming at you. Acronym, I don't know, weird saying. My integral of v du is equal to my ultraviolet super voodoo. Yes, it sounds weird, but it's hard to forget. So your UV, right? UV rays, ultraviolet. And your integral symbol is your super. And then you've got your VDU, you've got your voodoo. Yes, it sounds weird. But when I asked you on Thursday, you was like, oh yeah, ultraviolet super voodoo, of course. So we're going to get our u times our v, our natural log of x times x to the 6 over 6, minus the integral of our v times our du, which is x to the 6 over 6 times 1 over x dx. Okay, here's where you have to be careful. The whole point of this process is that the new integral should be easy, or at least easier. But to make it easy, you have to simplify it if you can. The x to the 6 over 6 times 1 over x, we can certainly rewrite as 1/6 times the integral of x to the 5th. Do the simplification. I've seen too many people say, oh, the integral of this is x to the 7th over 7 times the natural. No, we can't integrate the factors together and multiply the results. If we could do that, we would have done that from the beginning. It's not allowed. So then we end up getting the natural log of x times x to the 6th over 6 minus 1/6 times the antiderivative of x to the 5th is x to the 6 over 6. Let's see. And yes, we could simplify this, but so one thing to be aware of is when you have what most of us refer to as a mixture integral, meaning you've got two types of functions, usually consisting of two of these, a log and a power, or an inverse trig, and it's like two of these things. It's either going to be integration by parts, but it might be a u sub. So if you see an integral like, say, the integral of, I don't know, x times e to the x squared, before you start thinking about integration by parts, we should first see, can I do a u sub? And here you definitely could do a u sub. Here it would be a u sub with u equal to x squared and the du being 2x dx. And oh, we have an x dx, so definitely a u sub. In the same sort of way, right? So again, u sub comes up more when you have like a more complicated inner function. If you have a composition and the inside part of the composition is more complex than just x. Whereas integration by parts is going to come up when we have a multiplication of functions. So let me give you two more. I know we're almost out of time. Let's say we have the integral of x squared times sine of x cubed versus the integral of x cubed times sine of x. One of these is a u sub. One of these is integration by parts. I would like to hope it's not too hard to figure out which one's the u sub. Okay, left or right? Which one's the u sub? Left for sure. Definitely a u sub with u equal to x cubed. Whereas this one, we won't do it. We'll do it next time. This one is integration by parts, but it's sad because it's not integration by parts once. It's not integration by parts twice. It's integration by parts 3 times. And it gets a bit messy. There is a way to shorten that procedure, which we can talk about as well next time. But I'll just say for now, integration by parts 3 times.